Okay, so today we will discuss two classes of matrices, unitary matrices, and then positive, definite, positive, determinant. So we'll begin with unitary matrix. A unitary matrix is a square matrix. So we have a n by n square matrix U, and we represent U in terms of its columns. So U is this, U1, U2, all the way to UN. These are n-dimensional column vectors. Each of these U, each column of U is a n-dimensional column vector. This is U. The columns of U must be orthonormal for U to be a unitary matrix. By orthonormal, we mean that each of these U's columns of U must be a unit vector. Furthermore, they must be all orthogonal to one another. Okay? So the columns are orthogonal to one another, and they are also unit vectors. In other words, UI conjugate transpose Uj should be equal to 0 if I is not equal to j. So if Ui and Uj are two different columns, then Ui star transpose Uj, their inner product must be equal to 0. And if Ui and Uj are the same, that is I equals j, then we are looking at the same column vector, right? And since it must be a unit vector, Ui conjugate transpose Uj should be equal to 1. And what's a short way of denoting this? Kronecker delta, right? So Ui star transpose Uj equals delta Ij. Okay? That's what we mean by this. Okay, it's also called a orthonormal matrix. Okay, here's an example of a unitary matrix. U is this 1, 0, 0 is one column, 0 cosine theta sine theta, 0 negative sine theta cosine theta. So the three columns are U1, U2, and U3. U1 transpose U2. We won't do all possible combinations. Let's just look at a couple. So U1 transpose U2 is this 1, 0, 0 times this 0 cosine theta sine theta. And when you do this product, you get 0. 1 times 0, 0 times cosine theta, 0 times sine theta equals 0. U2 transpose U2. So U2 transpose U2 is 0 cosine theta sine theta, 0 cosine theta sine theta. So that's 0 times 0 cosine theta times cosine theta, cosine square theta, plus sine theta times sine theta, that's sine square theta. And we know that cosine square theta plus sine square theta equals 1. And likewise, U2 transpose U3, we can check that, let's say U2 and U3, their inner product is 0 cosine theta sine theta, 0 negative sine theta cosine theta. You see that cosine theta, negative sine theta, and then sine theta, cosine theta, they'll cancel out, you get a 0. And you can check the rest. So U is an example of a unitary matrix. Now, just a reminder, suppose we are multiplying two matrices. Okay, first of all, the inner dimensions must match. This is a 4 by 5 matrix, and this is a 5 by 3 matrix. Okay, so the inner dimensions, the first matrix, the inner dimension is 5, and for the second matrix, the inner dimension is also 5. So they match, and the dimension of the outer matrix the product matrix shall be the outer dimensions of the these two matrices. So it will be 4 and 3. So it's a 4 by 3 matrix. And how do we multiply? We take the ith row from the first uh, matrix on the left-hand side and the jth column from the second matrix to get the entry number ij. For instance, take this uh, first row, which is, I've colored it red, and the first column here, you see this is, which color is this? This is cyan. So red and cyan, that gives you this entry here. This red and this purple, row 1, column 2 gives you entry 1, 2. Row 1, column 3, magenta, gives you this. And likewise, row 2, which is this green, with this, row 2, column 1 gives you this, row 2, column 2 gives you this entry here, and you can match the colors. I've color-coded them for clarity, and so that's how it goes. Okay, and remember this for the next few slides. Actually, remember this always. So let's prove a few properties of unitary matrices. Lemma, the inverse of a unitary matrix is its complex conjugate transpose. In other words, U inverse equals U star transpose. Proof: we know from the property of unitary matrices, by definition of unitary matrices, a UI star transpose Uj equals delta Ij, where Ui and Uj are the ith and jth column of U. So U, the whole matrix U, U star transpose U. Now look at this U here. I'm expressing it in terms of its columns, U1 through UN. Now here I have U star transpose, right? So how do I take the transpose of U? So I have to take the star transpose of each of these and then arrange them in this manner. So each UI, when I take the transpose, it becomes a row vector, right? So U1 star transpose, U2 star transpose, and all are row vectors. And block matrices can be treated like regular matrices for the most part. So pretend that this is just a row vector. When you transpose it, you get a column vector like this, right? And that's why this is U star transpose. I have written it this manner. Now let's go ahead and do the multiplication. So U1 star transpose U1, then U1 star transpose U2, U1 star transpose UN at the last column. And then for the next row, I have U2 star transpose U1, U2 star transpose U2, and so on. Okay? So I get this matrix here, which is U star transpose U. Are you guys with me?
Yes.
Yes.
Now, what can you say about the diagonal elements? What can you say about U1 star transpose U1?
Identity?
It's 1, right? U2 star transpose U2 is 1. So the diagonal elements are all 1. And the off diagonal elements, U1 star transpose U2, because the columns are mutually orthogonal to one another, this will be 0. So all the off diagonal elements will be zeros. And just like Daniel predicted, so this is an identity matrix. So U star transpose U is, this is what we had, and this is the identity matrix. So U star transpose U equals I. Whence U inverse is equal to U star transpose. Agreed? The inverse has to be a unique a unitary matrix is always invertible, non-singular. So its inverse exists and is unique. Therefore, U inverse U equals U star transpose. Okay? And therefore, U star transpose equals I also, because it's the inverse. The rows of a unitary matrix are orthonormal. So I introduced unitary matrix as one whose columns are orthonormal. And now I'm claiming that the rows of a unitary matrix are also orthonormal. So let me represent U in terms of its row vectors. So V1, note that by default in this course, a vector is a column vector. So to denote a row vector, I'll explicitly use this transposition. So V1 transpose is a row vector, the first row of U. V2 transpose is the second row vector of U, and so on. And the last row of U is Vn transpose. Whence U star transpose is I first of all do the transposition of this one. So all these row vectors become column vectors, and then this block column vector becomes a row vector. And then let's not forget the complex conjugate operations too. So I get V1 star, V2 star, all the way to Vn star. So if this is U, then this is U star transpose. But U star transpose equals the identity matrix. This matrix and this matrix are inverses of one another, right? So I replace U with this and U star transpose with this. What do I get? V1 transpose, V2 transpose, dot, 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 Vn transpose times V1 star, V2 star, dot, 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 Vn star must be equal to I. Correct? Now, let me do the multiplication on the left-hand side. So this is what I have. V1 transpose, V1 star. V1 transpose, V2 star. All the way to V1 transpose, Vn star. That completes my first row. And then I obtain the other rows likewise. The last row will be Vn transpose, V1 star, all the way to Vn transpose, Vn star. And this we know is the identity matrix, right? Whence each of these diagonal elements must be equal to 1, and the off-diagonal or non-diagonal elements must be equal to 0. You see that?
Yes.
In other words, V1 transpose V1 star must be equal to 1, V2 transpose V2 star must be equal to 1, and so on. Whereas V1 transpose V2 star must be equal to 0, V1 transpose Vn star must be equal to 0, and so forth. Whence we see that Vi transpose Vj star equals delta ij. Okay? Or taking the complex conjugates, we can write this as, since this is just 0 or 1, its complex conjugate is delta ij itself. So on this side, Vi star transpose Vj equals delta ij. In other words, the rows of a unitary matrix are also orthonormal. They are unit vectors and they're all mutually orthogonal to one another. Questions?
Or just a simple question. The V vectors are rows or column vectors here?
The V's.
Uh-huh.
Well, in this course, a lowercase block bold lowercase will denote a column vector. To
Okay.
denote a row vector, I will explicitly superscript it with transpose.
Okay.
Okay, so each of these V1, V2, Vn, these are column vectors. V1 transpose, V2 transpose, Vn transpose, these are row vectors.
Oh, thank you.
Okay. The determinant of a unitary matrix is plus or minus 1. Proof. We just established that U inverse, if U is a unitary matrix, then U inverse equals U star transpose. Now, the determinant of U star transpose U, since they're inverses, this is I, the identity matrix. So the determinant of U star transpose U equals determinant of the identity matrix, which is 1, right? And let's call it equation 1. Now, from the property of determinants, the determinant of U star transpose U must be equal to the product of the determinants, determinant U star transpose times determinant of U, right? The determinant of the transpose of a matrix is equal to the determinant of the matrix itself. So we can ignore this transposition. So this is determinant of U star, right? The first factor here on the right-hand side is determinant of U star. But the determinant of the complex conjugate of a matrix, again, that's a property of determinants, equals the determinant of the matrix, its complex conjugate. So determinant of U star is determinant of U whole star. Okay. I think I should have added one more step here, but I hope it's clear. Any questions, or should I re-explain this little step?
No.
Okay, good. Anyone else? Is it clear? I need.
Yes.
I think it's clear, yeah.
Yeah,
Okay.
it's clear.
So that's my equation 2. Whence, from both sides, I get determinant of U complex conjugate times the determinant of U equals 1. Or the absolute value, actually there should be a square here, absolute value of the determinant of U squared. There's a typo here because I have determinant of U complex conjugate times the determinant of U. So that's determinant of U squared. Okay, this is a typo in my slide. Make sure that you make that correction. So this is equal to 1. So if the square of the determinant equals 1, what do you conclude? That the determinant is either plus 1 or minus 1, correct?
Yes.
The absolute value of the determinant is either plus 1 or minus 1. It could be a complex quantity, so you can have an absolute value of here too. So there were 2 typos here. The absolute value of the determinant. Oh, no. Determinant of U is plus or minus 1. Okay, norm preservation. Now, this is an important property. Okay, which is why unitary matrices are, which have determinants of 1, are called rotation matrices. Okay, in 3 dimension, they can be visualized as rotations. I'm not going to go into that. But anyway, so here's another property. unitary matrices preserve the Euclidean norm. What do we mean by that? So X is any non-zero vector. Then the norm of U times X is equal to the norm of X. And if A is any square matrix, then the norm of UA is equal to the norm of A. Okay. And this is why unitary matrices can act as rotations in 3 dimensions. You take a vector X, and UX is another vector. The length of UX and the length of X are the same. So it's only the direction that changes. That's why we call it a rotation. But if the determinant of U is -1, then it also involves reflection. Okay. But again, that's beyond the scope of this course. So this is what we mean by unitary matrices preserving the Euclidean norm. Okay, now UX, norm of UX squared, we are looking at the Euclidean norm now, is equal to, by definition, this is UX star transpose times UX, right? Which is equal to, now let me open up this parenthesis here, UX. So I'll have to flip the order of appearances. So X star transpose times U star transpose times UX, which is equal to, now I'll place parentheses here. So X star transpose times U star transpose U X. What we have within parentheses?
Identity.
Yeah. So since this is the inverse of U, and so we get the identity matrix. And so we'll end up with X star transpose X, which is the L2 norm of X squared. So L2 norm of UX squared equals L2 norm of X squared. Whence L2 norm of UX equals L2 norm of X, because the L2 norm cannot be negative. Okay. It follows that the norm of a unitary matrix is 1. Okay. You can take a unit vector here. Let X be a unit vector. What's the norm of a unit vector? 1, right? So U times a norm of U on this side will be equal to 1. And this is the definition of the norm of a matrix. And so this is a definition. So you can figure it out. This is equal to 1. And I'll leave this as an exercise for you to try out why this expression holds. Okay. But this is an important thing to remember, that unitary matrices preserve the Euclidean norm. Okay, another property. The eigenvalues of a unitary matrix lie upon a unit circle. Okay, so in other words, if we take the absolute value of any eigenvalue of lambda of a unitary matrix, it has to be equal to 1. Proof, let U be a unitary matrix, and let lambda and V be a eigenpair of U. And we know that we usually like to represent eigenvectors as unit vectors. So the norm of V is 1. Now, uv equals lambda v by definition, right? Whence the norm of uv is equal to norm of lambda v, which is equal to lambda being a scalar. I take it outside the norm, so which is equal to absolute value of lambda times the norm of v. Correct?
Yes.
Yes.
Now v equals 1. So this is simply, since the norm of v equals 1, so this is simply the absolute value of lambda. And that's my expression 1. Now, since u preserves the Euclidean norm from our previous lemma, we must have norm of uv should be equal to norm of v, right? It must preserve the norm of this vector v, should be equal to 1. That's equation 2. Now, comparing the left-hand sides of 1 and 2, we see that both are the same norm of uv. And so the right-hand sides must be equal. So absolute value of lambda must be equal to 1. That's the claim. The absolute value of every eigenvalue of a unitary matrix must be 1. In other words, it must lie on a unit circle. Questions? Next, the eigenvectors of a unitary matrix are orthogonal. Now, this proof is very similar to one of the things that we did and for symmetric matrices. So you should be able to do this proof on your own. Try it out. Now, I'll just briefly introduce you to a class of unitary matrices called group SO3. I'm not going to tell you what a group is, but this is relevant for quantum computing. But I'm just introducing this concept to you guys here. So this is Rx phi for where phi is any angle, and this is this matrix here, Rx phi. This is Ry phi, and this is Rz phi. These are 3 different kinds of matrices. It depends on what the values of phi are. Okay, and these are all unitary matrices, and the determinants are all 1. Okay, and you can check it yourself. Check that their determinants are all 1, and check that they're unitary matrices. You can try inverting a matrix and see what you get. I'll leave this as an exercise. The next topic is positive, definite, and positive semi-definite matrices. Positive semi-definite matrix Q. Given any vector x, if x transpose qx is always greater than or equal to 0, then the matrix Q is positive semi-definite, and we write it in this manner. X transpose qx is greater than or equal to 0 for every vector x. Okay, that's equivalent to saying that Q is positive semi-definite. And positive definite matrix, Q is positive definite, so for every non-zero x, x transpose qx is strictly greater than 0, then it means that Q is positive definite. And this is how we denote that. And likewise, negative semi-definite. X transpose QX being always less than equal to 0 implies Q is negative semi-definite, which also means that negative Q is positive semi-definite. And negative definite is similar to the definition of positive definite. So for any non-zero X, X transpose QX, if it's always strictly less than 0, then Q is negative definite, which also is the same thing as negative Q being positive definite. Okay? Now, if Q were a scalar, just simplifying things, if pretend that X and Q, these are all scalars, okay? What does this mean? Qx squared is greater than equal to 0 is the same thing as Q being greater than equal to 0, right? In terms of scalars. And for every non-zero X, if Qx squared is strictly greater than 0, then Q is greater than 0, right? So this has a very simple interpretation when we're dealing with scalars. So positive definiteness and positive definiteness, semi-definiteness, negative semi-definiteness, and negative definiteness are the matrix versions of scalars being greater than equal to 0, greater than 0, less than equal to 0, and less than 0. Okay? Now here's an example of such a matrix. Q equals 4, negative 1, negative 1, 1. Now let's have X equals this XY, and it's not equal to 0. So both X and Y are not 0 at the same time. Scalar X and scalar Y. X transpose QX equals this XY times this matrix Q here, 4, negative 1, negative 1, 1, XY. And upon simplification, this gives this 3x squared plus x minus y squared. Since both x and y cannot be 0 simultaneously, this quantity here can never be negative or 0, right? It's always greater than 0 because we have squares, thrice x squared and x minus y squared, right? So it's always greater than 0. Therefore, this matrix Q is positive definite. Did you follow this example?
Yes.
Yes.
Okay, now let's look at eigenvalues of these positive semi-definite and positive definite matrices. Eigenvalues of a positive semi-definite or positive definite matrix are positive or strictly positive. In other words, if Q is a positive semi-definite matrix, then all its eigenvalues are greater than equal to 0. Furthermore, if Q is a positive definite matrix, then its eigenvalues are all strictly greater than 0. Let's prove it. So let's do the first part. We assume that Q is a positive semi-definite matrix. And let lambda and V be an eigenpair of Q with L2 norm of the eigenvector V being equal to 1. Hence, by definition, since lambda and V are eigenvalues and eigenvectors, so QV equals lambda V. Correct?
Yes.
Now, let me pre-multiply both sides with V transpose. So V transpose QV equals V transpose lambda V, but since lambda is a scalar, I can move it to the left side. So this is lambda V transpose V, which is equal to lambda times, by definition, V transpose V is the L2 norm of V squared, right? So this is equal to lambda times L2 norm of V squared, which is equal to lambda because this is a unit vector. So V transpose QV equals lambda. Now, since we assume that Q is positive, semi-definite, what can we say about V transpose QV? Or for that matter, any X transpose QX? It must be greater than or equal to 0, right?
Yeah.
So V transpose QV must be greater than or equal to 0 since Q is positive semi-definite. Whence lambda must be greater than or equal to 0. Okay, and you can fill in the rest, the second half of this. Now, this is something I just included. We don't need this in this course, but for those of you who are doing control systems, you might need it. I occasionally need this in machine learning. But anyway, if A is a square matrix, then its exponential e to the A is defined as I plus A plus 1 over 2 factorial A squared plus 1 over 3 factorial A cubed plus dot, 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 all the way to infinity. And if this exists, okay, this is same thing as the Taylor series expansion, except that A is a matrix now. And so there are a few properties of the square matrix, sorry, the matrix exponential of a square matrix. Let me skip these slides. You can just look it up. We won't need this for the rest of this course. This is important for control systems. Here is the last one. Anyway, so recap of what we did. Unitary matrix U has excuse me, orthonormal columns. So U is, I represent this in terms of its column vectors, U1 through UN. Ui star transpose Uj equals delta Ij. The complex conjugate transpose of the unitary matrix U is its inverse. So U star transpose is the same thing as U inverse. The rows of a unitary matrix are orthonormal. Just like the columns, the rows are also orthonormal. So if Vi transpose is a row, okay, then Vi star transpose Vj equals delta Ij. So Vj is a column of U transpose, okay. Sure, decomposition we won't do. Anyway, unitary matrices preserve the norm. Norm of Ux equals norm of X. Norm of U, A, where A is a matrix, equals norm of A. Determinant of a real unitary matrix is plus minus 1. Determinant of U is plus minus 1. Actually, when we, in that slide, in the slide where I was trying to prove this, you should insert this real here. I was referring to a real unitary matrix. Absolute value of eigenvalues of a unitary matrix U are 1. So if lambda an eigenvalue of u, then absolute value of lambda equals 1. In other words, lambdas, the eigenvalues lie on a unit circle. Then positive semi-definiteness. So Q is positive semi-definite if and only if for every vector x, x transpose qx is greater than or equal to 0. And Q is positive definite if x transpose qx is greater than 0. Q less than equal, sorry, excuse me, Q is negative semi-definite if negative Q is positive semi-definite, and Q is negative definite if and only if negative Q is positive definite. If Q is a positive semi-definite matrix, then its eigenvalues lambda are always greater than or equal to 0. And if Q is a positive definite matrix, then its eigenvalues are all strictly greater than 0. And likewise for negative semi-definite Q and negative definite Q. Matrix exponential, I just give you the definition of a matrix exponential. We're not going to be very further than that. Any questions?
Nope.
Now, when you review these, you can safely ignore the star. We will always be referring to or dealing with real matrices and vectors. No questions?
No, Dr. Lara, everything is clear.
Okay, so this is going to be a quick lecture. Then, shall we end?
Yes, we can.
Yes.
Yes.